Powering data centers is a very real challenge, and that tech is changing. 12 volt and 48 volt power architectures won't cut it for modern data center power designs, so radical new DC distribution topologies are in development. So in this tech chat, sponsored by Mouser Electronics, I'm joined by Srijan Ashok from Texas Instruments to look into existing data center power architectures and explore how future data centers will be powered. We'll explore power supply unit trends and dig into how gallium nitride power stages are changing the game. Srijan, thanks for being here today. I'm excited for this.
Absolutely. Me too. I share your excitement, Daniel, and I think we are going to have a good chat, so looking forward to it.
So today we're going to dig into the world of data centers, which are changing faster than I've ever seen before. Could you talk us through kind of where we've been in the history of data center power and where you think this industry is going?
Absolutely. I totally echo your feelings there, Daniel. And I think at a high level, and we will maybe also talk through some of the slight details there as well. But at a high level, I think there are two major things that are shifting in the data center space. And these are very basic things when it comes to a power designer, but very important. I think number one is that the amount of processing power that I would say is needed to run a data center is increasing rapidly, primarily driven out of the AI revolution. Like we keep hearing about ChatGPT. And I think I don't remember the last time something pervaded my news cycle as much. Like everything today is like 15 minutes time span or attention span and we are done with it. But when it comes to AI, last 2 years of my feed on whichever social media platform I am on is all about AI, something new happening there, some new model, some new innovation. More recently, we had the Ghibli that's still going on, and I think it's increasing the GPU load. So I think all of this is really being done by all these major data centers that are, or rather all the processing that's needed to generate all these content, data, search results, images, are all done by these huge major data centers, and the workload is just increasing as the use cases keep growing, right? So that's the first point of like the power consumption is increasing. The second point is around the sustainability of it, right? Like if the power consumption goes up, you cannot keep like using the same designs that you were using, let's say for previous generation data centers, and keep the efficiency at the same levels and just run with it. I think there is a huge debate again about the whole sustainability aspect of data center as to how would you power these data centers. People are even looking at like very different ways to power it. Some people even suggested nuclear power plants actually to do it, but there are many more suggestions over there. But I think a critical aspect of it is how do you efficiently use every watt of power that's available to you. And I think that is what is causing the evolution as well. Like first of all is just the increased usage, and secondly is the whole how to keep the whole thing very efficient and sustainable and not hurt like real people in this case to power these data centers as well. So yeah.
Yeah, so there's more demand than ever, and even the amount of compute, had demand stayed flat, the amount of compute required has gone up. So what I'm hearing you say is that efficiency is going to matter more and sustainability is going to matter more. Can you walk me through kind of where have we been historically with data center power? And that I think will give us some good context for where we need to be today and tomorrow.
Absolutely. No, I think the slide kind of encapsulates it all. So initially, like the Gen 1, and we have stuck to this generation for a very long time. I think this generation has been there since pretty much data centers have been around, or rather servers have been around, right? So, but again, the workloads have been more recent. So coming to this, I think it's a traditional 12 volt architecture. It gets powered up either 3-phase or 1-phase AC, mostly 1-phase AC itself. And what happens is that you see this rack on the right, which has multiple shelves or blades as we call it. In that shelf itself, the AC power goes in, and there is a AC to DC conversion, which gets it down to 12 volts DC, right? Which is then given to the next stage of conversion, which eventually then powers up the GPUs of the future, I think, or the CPUs of the past, or whichever is the central processing unit. I think that powers it up. So the 12 volt is generated and then further, I would say, regulated down to the CPU voltage level, which typically is 1.8 volts, 1 volts. That can be, depending upon the CPU, you can have many many different voltage levels there. Now, the whole concept is that in this case, if you see, there are a couple of redundant power stages. One being the UPS, right? I think in the case of UPS, it connects to a battery, and there is UPS is nothing but when it comes online when the main power shuts off due to whatsoever reason, due to some glitch, etc. And then moment the power goes off, the UPS takes the battery power, converts DC to AC, and then it goes into the power distribution network. And then again at the rack level or at the blade level, it converts from AC to DC again. So I think there are two redundant conversion stages, right? Like the battery is converting from DC to AC and then AC to DC. So you tend to lose power. It cannot be 100% efficient there. So that is that. And then the whole concept of 12 volt flowing around, I think from an I square R perspective, because if you have a lower current, lower voltage, your currents will be higher. And as your current requirements goes higher, your I square R losses, or conduction losses as we call it, goes up. So I think due to these losses at some redundant power conversion stages and distribution, this tends to be 80% efficient from, I would say, grid to gate. So when basically the power just gets generated at the grid, and till the time it is delivered to the CPU, I think you lose around 20% of the power. So it's roughly 80% efficient. So yeah, that's how we used to do things, and that's how we are still, like, I think a lot of the current shipments are still in the 12 volt space. It's not gone off yet. It's still the majority, but definitely the share is now decreasing with the other voltage level coming, or rather increasing its pie in the cake. Yeah.
Okay, so we kind of have this efficiency stacking where every time there's some sort of conversion, you lose a little bit of efficiency,
Absolutely.
usually as heat. And then you're also doing DC to AC back to DC, which is theoretically we could bypass that altogether. And maybe it's more than theory. I know some people are also moving to 48 volts, and 48 volts has been kind of a new standard. Can you talk me through how did 48 volts improve over 12 volts?
Absolutely. I think great question. And I think it's segues right into how we are now thinking about efficiency, or how designers are thinking about efficiency and power density. So 12 to 48 volt, very simply, if I tell you, is 4 times the voltage level, right? To deliver the same power, let's theoretically say if it's the same power, you need 4 times lesser current, because power is nothing but V into I, right? So the moment you go to 48 volts, your I square R losses, because the I has now gone down by 4 times, I square can theoretically go down for the same power level by 16 times, because 1 by 4 square. So that, I think, is the first major advantage. And maybe some folks might also ask, why 48 volts? Why not then go to, let's say, 96 volts or 200 volts or some other voltage which is even higher and will further. So 48 volts is, from a safety perspective, I think 60 volt DC is what is considered safe for humans. And then 48 volt has some buffer to that 60 volt level. So it kind of is here, so that if there are some spikes, at least nothing exceeds 60 volts. So it's safe for human handling, I would say. So that's the reason 48 volt got chosen as a power level. Now, coming to how the efficiency also works, one thing I already told you is the I square R component. The other thing is now the way this particular architecture works is that again there is the same rack, and in the rack you see there are various shelves. Now earlier there was no power shelf, right? There was just all processing shelf, and within the processing card itself the AC to DC conversion used to happen in the 12 volt architecture, right? Now what's happening is that there is a power shelf that is like a central power unit which does the AC to DC conversion and generates the 48 volt rail or bus, and that bus kind of goes through the spine of the rack here, and then on that spine multiple cards or multiple processing motherboards get kind of plugged in. Now how that helps is, first of all, now you have more space on the motherboard because you're not doing an AC to DC conversion there. So AC to DC conversion typically involves a transformer, etc. you have more space on the motherboard to do more processing, right? It's just more real estate, and you can put like bigger CPUs, GPUs, whatever. And then that I think that 48 volt bus is now you can flow that bus in through the spine of this spine of the rack, because then your I2R component is lesser, so you can actually then take a bus bar and flow that 48 volt bus. And the other advantage is also that you can see that UPS kind of goes away. It becomes a BBU. Now, BBU is also a part of the power shell. Now, BBU is nothing but it interfaces directly to a 48 volt battery. And when the main power goes out, instead of doing a DC to AC and AC to DC conversion, it directly converts to DC, from one DC to another DC, and kind of translates the power from battery to directly to the spine or the bus that you have on the back of the rack. So you save in the backup power, you save in the I2R losses, you have a little more area to do more processing and compute on your motherboard. And then at the motherboard level, you get the 48 volt. There is an intermediate bus converter, or the IBC block that you can see, which converts from 48 down to 12. And then after 12 volt, it's the same story. There is another conversion which does to go down to the GPU or the CPU level. So you can see that the grid to gate efficiency now goes up to roughly around 85%. So you get 5% more efficiency out of just switching to this. And there are multiple methods again to further enhance it. But at the, let's say a good average would be 85%. Let's say you are 5% more efficient from grid to gate here.
And that's a significant improvement. Like 5% may not sound like a lot out of the gate, but we're talking megawatts of power here, and
Absolutely.
Megawatts of essentially heaters when there's loss, and that's going to contribute to increased, failure rates in the system if things are running too hot, and there's a whole slew of problems that show up with this extra temperature. So 5% is still quite significant. And it looks like the paradigm here is we're now putting power shelves right into the racks themselves instead of running the power they need from, another power system.
So I think, yes, you're right. And I think 5%, just to put things into perspective, I think nowadays an average AI rack is going from 100 to 250 kilowatts. So even if you take, let's say, 150 kilowatts as the average, 5% more power means around 7.5 to 8 kilowatts you save, right? Which in terms of wattage is a lot of watts right now. So that's just a perspective. This is just one rack in a data center. There can be multiple of them. So, and as you can see, it can be in megawatts. So the multiplication is just anyone's imagination. Then, yeah.
It becomes very clear why data centers are so loud. All the fans going.
Absolutely.
So beyond 48 volts, there's even more innovative things that people have figured out to improve efficiency. Can you talk me through kind of generation 3, our DC distribution state?
Absolutely. And just to give you perspective, I think today, most of the shipments or most of the data centers that are being deployed are still in the Gen 1 or Gen 2 space, right? With Gen 2 taking an increasing share. But now we are seeing an advent of Gen 3 because, as I mentioned at the start, there is an exponential increase in data center power requirements, right? And that would mean that the Gen to Gen movement and we are hearing of a Generation 4 already, which is even there, but that's still very nascent. But at least the Gen 3, the Gen to Gen movement the timeline has started shrinking. And I think it can be equated to any new technology revolution that has happened, be it mobile phones or laptops or anything. So talking about Gen 3, I think that same bus that I talked about, the spine of the rack, which was 48 volts, which was being converted by a power shelf, right? That is now becoming a high voltage bus. And now I know I talked about the 60 volt human level, I would say the safety levels. So again, with this, I think there is a component of machine interacting with the data center when it comes to actual physical placement, something like a kind of a robotic arm or something like that. But these are all just, I would say, talk right now. We don't know how the handling part of it will work very clearly, but we know what the buses are going to be, I think, to some extent. I think we are talking about 800 volt buses. Again, concept being the same, that when you increase the V, you can reduce the I, and then the I square R losses are more optimized. Or we are even talking about something like a plus minus 400 volt buses, right? And this, again, the choice of the bus is also dependent upon what power solutions and power topologies that you have to convert these very high voltage levels to something that the processor can consume, like to a low voltage, right? So a lot of different companies who kind of form the part of the OCP, the Open Compute Project, are debating on which voltage levels to land up in. And I wouldn't be surprised if there are multiple, like more than one voltage level. It's not just going to be like 48 volts. It's maybe somebody may go for plus minus 400, somebody may go for 800, some may go for 600 volts. So the field is split. But talking about how the conversion happens, so now the spine, as I said, is a high voltage spine, right? Whatever X voltage, 800 plus minus 400, two spines of plus and minus 400 or 600 or whatever. And that spine is now not generated by a power shelf, which is part of the same rack, right? We are now hearing that there is going to be a side rack architecture or a sidecar architecture, where the sidecar, the only job of the sidecar would be to do power conversions, right? So that will be like the power shelf, but now it's in a sidecar. And the main rack will just be a processing rack. So it will be multiple motherboard cards which will be plugging into the spine that gets generated by the side rack or the sidecar. And this AC to DC, and typically now the power will become three-phase AC. It won't be single-phase AC anymore. Three-phase AC to the high voltage DC conversion will happen in the sidecar. So BBU will be on the side car, and it will engage or interact with a battery which is high voltage. It can be for 400 volt battery. It can be, let's say, a 270 volt or a 150 volt battery, which converts to a 400 volt bus or a 800 volt bus, or whatever is the DC bus that the customer or the rack chooses to be. So the BBU, as you can see, has shifted from 48 volts to being a high voltage BBU now. And then on the motherboard itself, there are two power conversions that will happen before generating the 12 volt. The first one, because it plugs into the high voltage, and let's assume it's 400, it's going to be 400 volts. The first one would be a 400 to 48 volt conversion. It will be happening through very small DC modules, right? And the next one is going to be a 48 volt or a 50 volt to 12 volt conversion, which will then go into the further down, which will then be further down converted to the GPU power level, the VR stages as we call it, right? So to get to the VR stages, you will have two levels of conversion, the 400 to 48 and the 48 to 12. So the distribution losses will be drastically reduced, because you can see even if we go to 400 volts, that's like 8 times voltage coming down. So that's like 64 times the I square R losses coming down. So your bus bar size will shrink, because you won't need a big bus bar to manage the R part of it. So you can actually work with a smaller resistance of the bus bar. And that's I think the most major advantage here, right? And because now the main card will just have the processing here, so you get more processing space also. The power shelf doesn't take up any, it's on a sidecar now.
So we're essentially trying to move the high power components as much as possible, as close as we can to the motherboards, to eliminate the amount of current that's flowing from the power systems into the GPU cluster.
That kind of summarizes it perfectly. Yeah.
So three-phase will then go all the way to like the sidecar, which is, will it be kind of in a rack alongside the GPU clusters, or that's a lot more power coming a lot further into the data center than we've seen before?
Absolutely.
Are people worried about this or excited about this? What's kind of the response?
I think people are excited about this, but with anything new, there is also some anxiety when it comes to reliability, when it comes to let's say the safety aspect of it. How do you implement it? Like I just mentioned the word robotics, but it's easier said than done, right? You cannot just go and suddenly completely automate your data center with robotics right over there. So it's not an easy thing. It will require a lot of infrastructural investments. But there is a lot of traction, and looks like there are folks who really want to make this happen. And that gives us confidence that this definitely is going to take shape. Now, what we are seeing from the market is that looks like 2027 onwards is when it starts kind of going up, this type of a generation. And obviously, it will coexist with the 48-volt servers and the 12-volt servers. And it will just be it's just like, let's say, an increasing pie, and the share of this will also increase. There will be a 48-volt share also that will increase, and there will be some share decline of, I would say, 12 volts, but at the cost of these two generations increasing. But nonetheless, I think the pie is overall increasing. That's the good part. So I think people are excited. A lot of things to figure out with these high voltages. There is one more thing that comes into the picture is, and a lot of different power topologies, different devices that are needed to handle this kind of power. So I think that also is getting figured out. I think we do have some things that we are already pitching in this space, but it needs to, again, become more widespread than this. So I think that's also getting figured out. But again, a lot of figuring out is happening. That's why the percentage numbers, what's the efficiency increase is not shown here. But it's definitely going to be a significant percentage above the Gen 2 architecture.
Well, and if it had all been figured out, I think the whole industry would be mostly out of jobs. So thank goodness for unsolved problems.
Absolutely. No, I agree. I totally agree.
And you did mention the efficiency is notably absent. Do you have a feel for, is this another 5% sort of increase, or are we talking much higher than that, do you think?
I think it's a little too soon to tell. It should be north of 88 to 90%. Again, this is just my hunch. There's no, as I said,
yes,
plus minus 400 versus 800 versus 600, things will change in that itself. And then there are other things from a topology perspective that have not been fully figured out. So I think that's getting figured out as we speak. So I think those things will matter, plus what devices they end up using, the customers. I think those will also end up mattering. So I think the jury is out. Maybe in another couple of quarters, we will have a more clearer picture of what's the number going to look like.
Will we ever be able to go from like that 400 or 800 volt down to motherboard level without that intermediate 48 volt conversion, or is that 48 volts something that we need for the system?
Trust me that you're not the first person who's asking me this question, because I think there are quite a few conversion levels that are now happening between 400 to 48 and then 48 to the down level. So the other option would be that, okay, you take all this power and directly convert from 400 directly to 12 volts, or maybe even directly to the CPU level. The issue with that is the efficiency of that. First of all, most topologies, it's difficult to handle such high power levels directly in one stage, right? You need a couple of intermediate stages to provide the isolation that's needed, and maybe also some level of redundancy. But also, I think this is a very valid question, and this can still kind of happen. It's just that I think for now we are sticking, like a lot of folks are sticking to this architecture, that 400 to 48, 48 to 12, just to make sure that you don't change the entire thing from Gen 2. Because again, time is of the essence. So you have to kind of go to Gen 3 like faster. Maybe a Gen 4 or a Gen 4.5 will tackle that in one stage. But right now, if you see from the IBC onwards, it's the same architecture. Before the IBC is what we'll need to. Yes. So we are already kind of, a lot of folks have already optimized their architectures and efficiencies from the IBC downwards. So they want to keep it the same, change everything up there, make it like tune it to the highest efficiency possible, and then start looking at this again. So I think it's again, what part of the problem we want to solve. I think there are multiple parts to this. Yeah.
Yeah, that's fair. One problem at a time. Yeah. You mentioned we've seen very different amounts of power and different formats of power, from trays to racks to full sidecars. Is there anything that stands out to you here or that is particularly surprising for folks who are familiar and work with these power units every day?
Look at how fast the generations have moved. Like 1990s to now is 12 volt, right? Which is pretty much, I think, more than 30 years or 30-ish years. 2012 is when folks started up talking about Gen 2 and Gen 2.5, which is basically the 48 volt architecture. And 12 years hence, we have already started talking about Gen 3. So I think you are seeing that the shrink is happening of the time when we are thinking about these things. Right? It's almost 50% already. So yeah, that's
Yeah.
the one thing I would like to point out. Otherwise, whatever I have told you, like going from the onboard architecture to a spine-based architecture with 48 volts to going to a sidecar architecture with the Gen 3, I think it's all pictorially displayed here. Yeah.
Yeah, it is a good visual to see how different these things are and how fast the timelines are compressing. It's a very good point. We're
Yeah.
almost on a log scale of time here. So in 20 years, maybe it'll be like a 1-year cycle. Who knows?
Yeah. Then definitely we will need new jobs or
Yeah,
need
right.
faster ways to design these new generations because yeah.
So you talked about some of these trends already. Efficiency's going up, power consumption also going up dramatically, size is down, power density is going up. So I have to imagine your standard off-the-shelf power converter from the 90s is definitely not going to cut it today. What does a modern power system look like to get this sort of density?
Just talking about the PSU, I would say the power supply units, which basically do the AC to DC conversion, right? So earlier with the 12-volt PSUs, a lot of, so these are various, like PSUs do the AC to DC conversions. The onboard PSUs that used to go on the, I would say on the motherboard or power the 12 volts. There used to be a 12-volt spine architecture also where the bus has a 12-volt bus. So typically we would see a range of in the 12-volt spectrum in a range of, let's say, starting from 800 watts going to 2.4 to 3 kilowatts kind of range, right? And earlier, in the earlier gen, it was more 800 watts to 1.5. That only has now shifted towards 1.6 to 2.5 kilowatts in the 12-volt itself. Jump to 48 volts, we are seeing an increasing number of 3.6 kilowatt being deployed today and 5.5 kilowatts being designed today, right? These each PSU units. Now, multiple of these go in a power shell. So it powers up the entire rack. So let's say if a rack is 100 kilowatts, 20 of these 5.5 kilowatts with some redundancy may end up powering the entire rack. Switch to now, we are also working on designs, and TI has released a design on TI.com, which is 8 kilowatt. And using that, we are actually leveraging to build 11 kilowatt and 16 kilowatt designs with some projects with some of our customers. So you can already see that I started talking about 800 watts and I'm already at 16 kilowatts. And this is just the 48 volts. I have not even started talking about the 400 volts where initial conversation is all 20 kilowatt plus. So
Oh my goodness. Okay.
You can imagine how things are just becoming bigger in power. But again, actually you have to keep the size in the similar region. You cannot blow up the size by, let's say, going from 800 watts to 8 kilowatts. You cannot blow up the size by 10 times. You maybe can have two times to deliver that much same power. So power density clearly needs to go up. So I think that's how the spectrum is moving now. I think with till generation 2, it's much more clearer how things are going to move. Gen 3, as I said, the indication is 20 kilowatt plus, but the jury is still out. We are still engaging actively with many customers there.
So clearly there's a unprecedented hunger for more power in smaller and smaller form factors or power densities. What is TI doing to help address that, and how is TI powering the new data centers?
So I think TI has invested pretty significantly with our new gen GaN devices. I think we have launched quite a few devices in that portfolio, which if you see all the colored blocks that we cover, going right up to the 12 volts, starting from the 1-phase AC or 3-phase AC. You have majorly 4 blocks, which is basically PSU, which does the AC to DC conversion. Now the DC can be 48 volts or 400 volts. Then we have the VBU, which can be a high voltage VBU for Gen 3 or 48 volt VBU for Gen 2. Then we have the IBC modules, which we have basically does the 48 volt to 12 volt conversion. That's available in both Gen 2 and Gen 3. And then we have the high voltage DC to DC modules that go on the motherboard, which basically takes the high voltage and converts it to the 48 volts, which then goes into the IBC module. Now, for all these blocks, TI has parts, which is simple to understand, but we also have built quite a few reference designs, right? And if I talk about parts first, I think both in the high voltage and medium voltage spectrum, we have invested significantly. We have the first three items talk about the high voltage space. So we have 650 volt parts with QFN and more recently launched toll package on TI.com. And these kind of help you in achieving a really high power density. And all these devices come with an integrated gate drive. So with GaN, the gate drive circuitry becomes a little critical, right, to design. But if you integrate that and just ask the device to sync with the MCU or the PWM controller, then your design becomes much more simpler, very power dense, because you don't have to lay out the extra driver with all the fault detection features, because this has all of them integrated again, like overcurrent, over temperature fault, under voltage lockout, etc. And even some advanced features like zero voltage detection for dead time optimization and to kind of manage that as well. So I think TI hasn't just released a power device, it has released an integrated power stage, which makes it really easy for a designer to take it and design their subsystem. We also have 100 volt parts now. We have released like 2 devices. And here we have in fact also integrated a half bridge, which basically means 2 FETs in one package with the level shifter and gate driver all integrated in the package. So again, when you're going, because these design cycles are now going down, when a designer is going to a new design which requires more efficiency, more power density, wants to use GaN, adopting these become very simple, right? And you can do it at a very efficient layout, very high power density, because we take care of a lot of the critical features that are around the gate drive design, right? And also around the fault reporting, which our devices kind of have in it. So a lot of exciting stuff already released, but a lot more coming out. I think 2025 is going to be the year where we really blow up our portfolio and keep an eye out for whatever is happening on TI.com. Yeah.
Sounds good. So some big and exciting things coming from TI that we'll maybe not find out about today, but 2025 will be a banner year for you. That's what it sounds like.
Absolutely. Absolutely.
Love it. So really at the end of the day, we care a lot about efficiency, and that's something that you're working towards. We care about power density because you don't have all the space in the world. You got to fit inside a data center, which is already super cramped and getting more and more cramped. And then you also are able to integrate all the fault detection features, the gate driver, and some of these other things that a designer would have to typically think about and provide space for in their footprint of the board, but it's all in the integrated circuit itself. It's integrated.
So I think, yeah, you have excellently summarized, and this slide kind of is for that. Efficiency, power density, and to achieve that, use TI GaN and I sound like a very typical marketer here, but the reason is right in front of you, that it gives you a very easy time putting GaN into your designs and achieving the efficiency and power density goals by just integrating all the smart features and optimizations into one package. So yeah.
So if people are wanting to integrate these systems into their designs and into their servers, where should they go, and what sorts of things should they be looking for as far as like reference designs or resources to help them be successful with this?
So I think the first place is to go to ti.com/GaN, GaN, stands for gallium nitride. I think that's where our portfolio exists. And when you go to the different devices, all these different designs that you see on your screen for the different subsystems, be it the PSU, for the IBC, for the BBU that I showed, and that you showed in the slide a couple of slides before. So that will all be as part of the devices product folder. You can just go and look at these reference designs, and that's what the other area of investment is. So when we say that we have come up with these excellent devices, we just don't leave you at that. We also have created all these very good reference designs, and we have a very, I would say, solid base of power experts within TI. And we have a power design team who have created these designs, and these have been tested. And the BOM schematic and the Gerber files are all available on TI.com. So anybody who wants to really get quick start and really understand how the system works, and you can just look at these test reports as well, and then just import these files and start using them and maybe tweaking them and creating a design around them. So otherwise as well, for more, I would say, seasoned power designers, this also serves as a very good proof point that, okay, how does GaN really help in improving efficiencies and achieving really high efficiencies in a very small form factor? So I think These designs all demonstrate efficiency and power density. And please go and take a look. This is not an exhaustive list. This is what that could fit on a slide. But these are the newer designs. So just take a look and reach out to your respective sales folks to further the discussion there.
Well, thank you so much for being here. I'm super excited to see where this goes for Gen 3 and maybe even Gen 4. Who knows when we're starting to get to kilowatts or kilovolts of supply power, but we'll have to watch the watch the folks and see what happens.
Thanks, Daniel. It was very great to talk to you and share whatever I know about the space.
Thanks for tuning in to this tech chat brought to you by Mouser Electronics. That was Srijan Ashok from Texas Instruments. If you'd like to find those reference designs or get some of these for your next project, head over to mouser.com/TI. I'm Daniel Bogdanoff, and I'll see you next time.